I'm really excited to be here. Thank you, Zishan, and all the sponsors and everyone who works on PapersWeLove, because this is an amazing project. And I remember when it popped up, and just there was like so much enthusiasm around PapersWeLove. There was clearly a very strong desire to read academic papers and talk about them. I have no idea why you guys want to do this, but you know, that's cool. That's great. I mean, I support it. This is really awesome. So I'm here to present this paper today. And Zishan said I could pick anything I wanted, and there are a lot of really amazing old papers out there, but I really wanted to do this one. So this one's super new. It came out a couple years ago, and it very quickly took my community by a storm, I'd say. It won a Best Paper Award at the conference, and more importantly, Austin, the first author, he won a Best Thesis Award, which is like really impressive. And people really like this piece of work, and I think it's really cool, and it has a lot of applications to distributed systems and operating systems, and yeah, so we should talk about it. Okay, so this is called the Scalable Commutativity Rule, and it's by Austin, Clemens, Franz Kashuk, Nikolai Zeldovich, Robert Morris, and Eddie Kohler. Okay, so first a little bit about me. I have nothing to do with this paper, by the way, even though it's from my lab. I'm a PhD candidate at MIT, and I'm working on high-performance concurrency control in databases and distributed systems. And so the question that I really want to answer is, how can we get high performance and strong consistency? So what are the kinds of tricks we can play? How far can we push it? I used to work at Google a while back, and this is some information about where you can find me on the internet. Okay. So a few caveats before we get started with this paper. So number one, I sat about 10 feet away from the author of this paper for 6 years. And my advisors are the last two authors on this paper. So I might be biased, but like I said, I had absolutely nothing to do with it. And the second caveat is that I'm totally obsessed with commutativity right now. So, you know, this paper has a lot to do with commutativity. I've been thinking about commutativity a lot recently in regards to how we can get faster concurrency control in databases, and that's part of why I wanted to present this paper. This is what comes up when you Google search for images on commutativity. Anyway, okay. So here's the paper. This paper was presented in SOSP, and like I said, won a ton of rewards. And here's the outline for how we're going to talk about it. So first, I'm going to present the problem that this paper addresses. Next, we're going to actually talk about the scalable commutativity rule, and we will try to understand it intuitively and then a bit more formally. Then we're going to talk about how you can apply the rule to actually get something useful out of it, and then we'll sort of go off in speculation. We'll talk about the limitations of the rule and maybe where else it could be applied. Okay, so let's start here. So Moore's law is over, or at least it's going to be over pretty soon. We're starting to reach the limits of how many transistors we can actually fit on a chip, both physically and economically. So what this graph shows right here, we've got time on the x-axis and number of your choice on the y-axis, either megahertz or watts. And what this is showing is that really the number of megahertz that we're getting out of our chip has been leveling off over time. But in some ways that's okay, because we've been adding more cores to each socket. So maybe each processor isn't getting that much faster the way it used to, but we can put a lot of them together in one socket, and that yellow line up there shows that in terms of total megabytes or megacycles per second, we're still getting a decent performance improvement. But that performance improvement has to come from parallelism now. And that's a serious problem, because writing parallel software is extremely hard, especially operating systems. So applications all depend on the operating system, and the whole point of the operating system is to mediate access for lots of different applications to the same resources. The Linux developers, in particular, have spent many man-years working on making Linux more scalable. It is extremely challenging. And so what this graph right here shows, on the x-axis is number of cores. So we're running two applications, GMake and XIM, on a multi-core machine, and we're increasing the number of cores. And the y-axis is throughput. And what we see here is that GMake, cool, we totally scale. Add more cores, get more performance. That's exactly what you want to happen. However, GMake is like super easy to parallelize, make, right? You can do a bunch of files at the same time. XIM, the mail server, unfortunately, things look pretty good up until 24 cores. And what's interesting here is they really do look good up until 24 cores. And then we see this dramatic crash. And that dramatic crash is actually caused by one contended cache line. And so what this shows, what's so amazing about this right here, is that one contended cache line can completely ruin the performance of your application as you scale up the number of cores. And also, something a little more subtle, but also very interesting, is that you won't even be able to tell that that's going to happen until you get past a certain number of cores. And then things will just drop off dramatically. And so you may be wondering, well, why is one cache line so important? Like, what's going on here? And so we have this nice graph. And this graph shows, on the x-axis is the number of readers. So there's one writer. There's one thread writing, and there's n different readers on different cores. And the y-axis is the amount of cycles that that read takes. And so what we see here is that a cache line, it can actually take a really long time to do a read if that cache line is bouncing around a bunch of cores. It makes each read take a lot longer. In fact, it rises linearly with the number of readers. And that blue line right there on the graph is the amount of time that the open syscall takes. So reading a contended cache line is extremely expensive. So the way that developers deal with this right now is they go through this cycle. They go through this cycle of benchmark my code on however many cores I have, figure out where the bottleneck is, redesign my code to get around that bottleneck, and then try again. And they do this over and over and over again. And I mean, the good part of this is that they're fixing real problems, right? They're fixing problems that they actually see on a lot of cores. But the bad part is that it's really difficult to tell what problems might arise in the future. And the really tricky thing that this paper addresses, which is awesome, is that the bottlenecks might not just be in your implementation. They might actually be in the entire interface design of your software. So let's talk about scalability for a second. What actually does scale on today's multi-core machines? Well, today's multi-core machines use the messy protocol to handle cache coherence. So they're all doing cache coherence for us, and the hardware is actually taking care of invalidations and putting cache lines into the proper modes. And generally on today's hardware, reads don't conflict, but reads and writes, or writes and writes, do conflict. And so what that means is that, and in addition to that, conflict-free is a good proxy for scalability. So basically, if operations don't conflict, it means that you can probably get good scalability out of them. And so this sort of derives this insight: two operations are scalable if they are conflict-free. But note that this is just an approximation. It's totally based on the hardware. So if we had different hardware running a different cache coherence protocol, we might get different results. And so it's just important to note that that's what this paper is predicated on. All right, so that's the problem. And now we understand the problem. We want to write scalable software, and that's really challenging and time-consuming. One cache line can totally destroy the performance of our entire application, but we do know a little bit about the properties of the hardware we're running on, and we do know that we can probably get scalability if we can make operations conflict-free. So that's where the scalable commutativity rule comes in. And to understand a little bit about what this rule is talking about, let's look at this example. Okay, so this example tells us about what it means for an interface to scale. So this is three operations. We're calling create 3 different times with 3 different names, and this is going to return file descriptor numbers. So it's like we're opening 3 different files. Okay, so the way that create is specified, like in the POSIX specification, is that create should return the lowest number file descriptor that's not currently in use by this process, okay? So here, if we ran the 3 operations that I'm showing you up there, then these 3 calls should return successively higher file descriptor numbers. Now, the problem with that is that in order to ensure this, we have to do some funniness in the implementation. We probably have to take out a lock on the entire list of available file descriptors. We need to make sure that the create on X gets the lowest file descriptor number because Y and Z are coming later. And so we need to take out a lock and make sure that it gets the next one. And this is kind of unfortunate because the create on X blocks the create on Y and the create on Z, even though they're opening completely different files. You could imagine a different specification for this system call that didn't have this lowest file descriptor number constraint. So what if create could return any file descriptor number? Well, then we probably wouldn't need that global lock. We could do something like this. And what's going on here is that each create call could try to get some numbered file descriptor. And if it got it, awesome, great, it's good to go. If it turned out somebody else had already gotten there first, no problem. Try again with some other random number. Much less likely to conflict, and there's no single lock going on here. So this is some of the intuition behind the scalable commutativity rule. So the scalable commutativity rule says whenever interface operations commute, they can be implemented in a way that scales. So let's take a look at our version of create, which has to return the lowest file descriptor number. Okay, so if we issue 2 calls to create, what happens? The first one needs to return 1 lower than the second one, right? Does this commute? No, you can totally tell the order they happened in, right? The one with the lower file descriptor number happened first. Okay, no good, does not commute. What about our version of create with any file descriptor number? Does that commute? Totally, right. It doesn't mean anything that one returned 13 versus 47. You're just getting random unique numbers back. Once both of these have executed, you can't tell what order they happened in. So great, they commute. And what the rule says is because they commute, a scalable implementation exists. And we know what that implementation is. I just described it a little bit earlier. You could imagine like locking numbers that you're choosing randomly and only trying again if there was a conflict. So that's the intuition behind the rule. When operations commute, the results are independent of order, communication is unnecessary, and without communication, there's no conflict. Okay, so let's try to understand what we mean by commutativity here, because the definition of commutativity in the paper is very different than any definition of commutativity I've ever used, if you guys know that. It's a little specialized. So one thing that makes it a little bit different is that it's not just about operations. We all know addition is commutative, multiplication is commutative. This is about operations that take arguments and return results. And the commutativity of operations is actually dependent on both of those two things. And the thing that's really nice here is it actually broadens up what we can consider commutative, because there's a lot of operations that don't commute in all cases, but might commute with the right arguments. Like add and multiply commute if you're adding 0 and multiplying by 1, right? You still get the same number no matter what. Whereas normally, without thinking about the arguments, add and commute definitely, or add and multiply definitely do not commute. Okay. So let's look at what's going on here. Here we're using the example of a reference counter. So we've got 5 different cores, and we have 2 operations. One is called is0, and it just tells you true or false whether or not the reference counter is 0. And then the other is decrement, and decrement is returning the value of the reference counter after it does the decrement. Okay, so here's a little test. Is this region of the execution commutative? Yes, right? You could swap the is zeros, doesn't make any difference. They both return false. You can't tell what order they executed in. Cool. Okay, and because of the rule, we know that it has a conflict-free implementation. One example might be a shared counter. So even if you just have one shared counter, reading it, 2 processes reading it doesn't conflict, right? So that's an example of an implementation that for this specific region would be conflict-free. All right, how about this region right here? Is this commutative? Nope, definitely not, right? Decrement is sadly returning a number. You know that these numbers need to happen in order, and so therefore it's not commutative. Okay. But what if we had a slightly different version of decrement that instead of returning the value of the counter, returned okay when it did the decrement? How about now? Is R2 prime commutative? Yes, right? Definitely looks commutative to me. It's just decrement, okay, decrement, okay, decrement, okay. Awesome. And we can also think of a conflict-free implementation of this. We could imagine a per-core counter. So we could take the shared counter and partition it among a bunch of cores, and they could each do decrements locally until they get to 0, and then they'd have to talk to each other. Cool. Okay. What about the whole region? Is the whole region commutative? How many people think no? How many people think yes? All right, no, just for the video, no is like way higher than yes. It depends, and it totally depends on the state, okay? So what's happening here is that if the value of the counter is greater than 3, then this whole thing commutes. You could do the is 0 after all the decrements, you could like reorder them in any way, and it totally commutes. But if that counter is less than or equal to 3, then if is 0 happened at the end, it should return true. So this is like a really great example here about how the arguments and the return values in the state can define commutativity, and how you can get commutativity sometimes for specific states. So even like the same sequence of operations and arguments, depending on what the state is, they might be commutative or they might not. Okay, cool. So now let's talk a little bit about formalizing the rule. So we learned a little bit about regions and state-based commutativity. And so now we're going to go over some of the definitions in the paper, and we're going to try to formalize this. Okay, so the paper talks about histories. So a history, H, is a sequence of invocations and responses on threads. And basically, it's like you call a function, that's the invocation, you get some response back, and that's the response. So ideally, an invocation and a response would happen on the same thread. And they use these like nice little colored offset things in the paper, if you've read it, to sort of try to designate which thread is issuing what in what order. Okay, so here we have 2 threads, T1 and T2. Each has an invocation. So T1 is calling increment and getting OK back, and T2 is calling is 0, and in this case, getting true back. On the left side, we have what is called a legal history. Okay, this makes sense. Is 0 returns true, it's 0, but then the increment happens after the is 0, and so it gets an OK. So that makes sense, that works. It could have been 0 before the increment. On the right is an illegal history. There is no way that is 0 should return true after an increment. An increment just happened, right? So that's an illegal history. And we're assuming these are the only things in the history. We're just talking about these operations right here. So a specification, Zeta, and I think he might have used a slightly different Greek symbol in the paper, but I couldn't find it, so whatever, we're using Zeta. Okay, a specification, Zeta, defines an interface. And Zeta is a set of legal histories given the allowed behavior of the interface. And so Zeta is a set of all possible histories that make sense. That's it. It's just a way of like talking about everything that could possibly happen that fits the specification. So the reason we need this is because we want to talk about commutativity and conflict freedom and whether or not we can scale without actually getting into implementation details. And so by doing this, we talk about what an interface allows without actually getting into the details of how it's implemented. Okay, so a reordering of a history, H prime, is a permutation of H that maintains operations order for each individual thread. And so that's the notation you use to write that. So for each thread in H, its operations happen in the same order in both H and H prime. However, they could be interleaved among each other in different orders. So that right up there, that's like basically the same as H. Here's an H prime, which kind of moves things around a little bit. Here's another one. This one is not legal. So this is a reordering that's not legal. Okay, so now we can talk about the very specific definition of commutativity that they use in the paper. So a region Y, and we looked at regions before, it's like a part of the history. A region Y of a legal history XY sim commutes if every reordering Y prime, so every way of reordering all of the operations that happen in Y, it also yields a legal history. That means that it fits the specification. And every legal extension Z is also a legal extension of XY prime. So what this is really saying is that a region Y is commutative if no matter what comes before it and no matter what you stick after it, that region, you still get a legal history. So it commutes no matter what comes next. There's no way in the interface to tell what order the operations happened in Y. That's what this is saying. All right, and now we have the formal rule. So let Zeta be a specification with a reference implementation M. And so the idea here is that M is just any reference implementation whatsoever that happens to implement the specification that you gave it. And remember, a specification is the list of all possible legal histories. Consider a history where xy, where y commutes in xy and M can generate xy. Then there exists a correct implementation of Zeta whose execution of xy is conflict-free in the commutative region y. Okay? So this is the formal rule. And what it's saying is that when you have this case, where you have this sim-commutative region y, then there is some way to do a conflict-free implementation for that region. Not before that region, not after that region, just for that region. And it's one implementation per region. They might be different for different regions, and I'll get into that a little bit more later. So the proof that they use is constructive. So what they do is they actually construct the conflict-free implementation in the paper, which is very confusing. And so it's based off of the reference implementation. And the way that they do that is that basically the conflict-free implementation just emulates the reference implementation until it gets to region Y. And then once it gets to region Y, it stops emulating the old reference implementation and instead just starts doing stuff per thread. And then when it's ready to start emulating the reference implementation again, it kind of has to fast forward. But the point is that just during Y, you were doing stuff per thread. You didn't have to keep track of order. And keeping track of order is really what caused us all those problems and created a non-conflict-free implementation to begin with. So that's the general intuition about how they do this construction. Okay, cool. So we have the scalable commutativity rule, but that's only like half the paper. There's another half of the paper which is about how they apply the rule. And it's pretty amazing. So they built this tool called Commuter. And Commuter, you write your specification of the interface in Python, and then Commuter will tell you whether or not there's a conflict-free implementation for your interface for specific arguments and specific return values. So this is kind of amazing. Like it does this like symbolic execution thing, and so you give it your interface. You have to write your interface in Python. That's true. You got to do it. And then Commuter is going to come out with not only the specific cases where your interface could commute and therefore there's a conflict-free implementation, but you can also give it an implementation and it will tell you where it's not conflict-free. So let's take a look at how Commuter works. So the input you give it is a symbolic model, your Python specification. It's got an analyzer that runs the symbolic specification using a SAT solver and computes commutativity conditions. And then once it has those conditions, like as long as these renames are not on the same directories, basically. It comes out with sort of like, as long as this argument isn't equal to that argument, then this computes. It comes out with stuff like that. Then it uses testgen to compute test cases. And then finally, you can give it those test cases and your implementation, in this case, Linux, and to mtrace. And mtrace will actually run your implementation and tell you whether or not you have conflicts for things that don't necessarily need to conflict. And it comes out with exactly where those conflicts are. So this is amazing. This is like the full circle of tools. It's like, this is how you apply the rule, this is how you run it, and here I'm just going to tell you exactly what you need to fix with your implementation. So let's go through an example of how this works. Let's look at rename. Oh, that shouldn't say neither. I don't know what's going on. Okay. This is not right. This is really weird. Okay. Okay, cool. I don't know what's going on there. Anyway. I mean, it wasn't just me, right? It didn't look like that before. Okay, good. All right. So, Microsoft. Anyway, so here's rename, okay? So two rename operations. Let's think about when those rename operations actually commute. So what will happen is that the analyzer will spit out this list of conditions. So when both source files exist and their names are different, When neither source file exists, returns an error, 2 errors, commute. When A or XOR C exists and it's not the other's rename destination, so these are, I mean, one call is a self-rename of an existing file and A doesn't equal C. A and C are hard links to the same inode, A doesn't equal C and B equals D. Both calls are self-renames. And what's important to note here is that it's actually kind of important to have discriminative commutativity conditions, because for all possible states, rename almost never commutes. It's not the case that rename's going to commute, right? And so if we were just thinking about like commutativity in terms of operations, we would just have to throw it out the window. Rename doesn't commute, oh well, no scalable implementation. But by looking at the arguments in state and coming up with these conditions, which actually, if you look at them and think about them, aren't totally unreasonable, right? Like, it's not like it's saying, if this directory happens to be like 3 levels deep from this other directory, no. I mean, these things kind of make sense, right? Like, if both renames would return an error, they commute. If all the names are different, you're doing like completely different sets of things, then they commute. That makes sense. And the more commutative cases there are, then we have more opportunities to scale. And this is capturing stuff that applications actually do. So then they have this awesome graphic in the paper. So they ran Commuter on Linux. And so what this shows is it's like a heat map of pairs of operations, pairs of system calls from Linux, and how many conflict-free tests they had and how many conflicted tests they had. And so what we see here is that Commuter generated 13,664 test cases, and 68% of Linux, for 68% of those, Linux was conflict-free. So here's like what those red areas up there are, the ones that were super not conflict-free. Linux uses directory-wide locking. So as I showed you with the rename example, sometimes you don't actually need to lock the directory. For example, if you're renaming totally different sets of files, but Linux does. File descriptor reference counts to do that whole lowest file descriptor number thing. And Linux also does address space wide locking. And so that's where most of those red regions came from. And just to be fair, this paper was like actually presented 2 years ago, and the work was done maybe 3 to 4 years ago, and so it was run on a slightly older version of Linux. It was 3.8, and so a newer version of Linux, they might have fixed some of these scalability bottlenecks. Oh, no? Okay. So they wrote this new operating system. So not only did they come up with this rule and formalize it and give you a tool, they were like, well, let's just write a scalable operating system. So they did. Though to be fair, these guys have written a lot of operating systems, so maybe it's not hard, like the nth time. Okay, so they wrote this operating system called SV6. It's a scalable operating system, and it's POSIX-like. Its file system and its virtual memory system follow the commutativity rule, and its implementation uses pretty standard parallel programming techniques, but the design of this operating system was partially guided by Commuter. And so here's the heat map for their operating system. Whoa, right? So again, 13,664 test cases, 99% are conflict-free. The remaining 1% are mostly idempotent updates. So everything in your operating system should not be commutative. That doesn't make any sense. There should be some non-commutativity in your operating system, right? You just want to reduce it so that it happens as little as possible. And so here, the remaining 1% of idempotent updates were when 2 L-seeks of the same file descriptor go to the same offset. Yeah, it seems like those probably shouldn't commute. Or when 2 P-writes of the same data to the same offset. Again, it seems like you've got to do some coordination there to make sure that they don't overwrite each other. Okay. And so here's where they really got a benefit from these techniques. This is how they refined the POSIX interface using the rule in order to get better scalability. So here are some of the things that they changed. So first of all, that file descriptor thing. No need to return the lowest file descriptor. Most developers don't really depend on this behavior. It's usually okay to return any file descriptor. Similarly, there was an example with stat versus xstat. So when you call stat, you get a whole bunch of information about the file back. You probably don't need all of that information. You need maybe one field out of that information, and so why not ask for that specifically? It introduces more opportunities to commute. Sockets order everything. Sometimes you don't need that to happen. munmap, when you call munmap, the kernel actually makes sure that it's released its memory before it returns. That's not necessary either. Hardly any behavior relies on the fact that when the munmap returns, that memory is no longer accessible. And then they have a good example in the paper about fork and exec versus POSIX spawn. Basically, fork, since it takes an entire copy of a process and creates another one, it doesn't commute with very much at all. But if you're just going to blow away that copy and replace it with a new program anyway, then that combination of operations does commute with a lot. And so looking at these specific examples, we get sort of the following lessons that we could learn when we're designing our interfaces. So the first one is embrace non-determinism. There's no need to get the lowest file descriptor number back. Any file descriptor number will do. And so if it makes sense, don't use things like ordering, right? Decompose compound operations. So I believe that this is the stat versus exstat example. Permit weak ordering. This is the sockets example. And finally, release resources asynchronously. It's okay if you don't release the resources before the operation returns. Okay, so then they show that commutative operations really do matter. So that green dotted line at the bottom, well, the x-axis is number of cores, and the y-axis is total emails per second. They're running something like QMail. The green dotted line at the bottom is something with non-commutative APIs. The lowest file uses the lowest file descriptor, ordered sockets, fork, and exec. And as you can see, it really doesn't scale very well at all. The red line is using these features, right? Commutative APIs, any file descriptor, unordered sockets, POSIX spawn. And on an 80-core machine, it scales pretty much linearly. Cool. Okay, so if you want to learn more about this, I suggest reading Austin's thesis. It's really good. He put a lot of time and energy and thought into it, and it has a really great explanation of everything that's going on in the paper. He got to go a lot deeper. And so now I want to talk a little bit more about sort of what the rule isn't saying and what it might mean for different contexts. Okay, so here are some limitations of the rule. And this is in the paper and in the thesis. It's not like I'm coming up with this by myself. I just wanted to let you know that. So the rule says that a scalable implementation exists for a commutative region. It doesn't say anything about, how fast that implementation is, what the raw performance is. It also says that a scalable implementation exists. That doesn't mean that that implementation would be good for a different commutative region. And so what the rule is really telling you is that for a very specific history, a very specific set of arguments and state, you can find an implementation that scales. But unfortunately, it might be super specific. It might be exactly tuned to that specific region. And also, it's really unclear on how to find this implementation, right? So I did a little bit of thinking about this, and what I realized was maybe the implementation you use for the commutative region actually puts more work on you when you get out of the commutative region. Like maybe you need to put a whole bunch of stuff together again that you were initially, during the commutative region you were writing separately per core, and maybe that's really expensive. So this doesn't say anything about raw performance. It might be the case that a non-scalable implementation gets better raw performance. So they thought a lot about this, but they weren't able to show the non-scalable non-commutativity rule. So the scalable commutativity rule says a scalable implementation exists if the region's commutative. It doesn't say that there's no scalable implementation if the region's not commutative. And in fact, this probably isn't true. We can think of like trivial examples where the region's not commutative, but we could probably come up with a scalable implementation. And then finally, all of this goes out the window if you have synchronized clocks. Because with synchronized clocks, you can get ordering without communication. And so there was actually another paper thesis by someone in my group who worked on exactly how to do that, how to sort of log operations per core using synchronized clocks to understand what the ordering should be and then put them back together later. So one thing that I'm really interested in is what applications this rule has to distributed systems and databases. So distributed systems are just a different world than multi-core operating systems. We don't have cache coherence. There's no hope for a synchronized clock, unlike on a lot of highly multi-core machines, which actually do have timestamp counters. So in the distributed systems world, the paper says a little bit about this. Reads still don't conflict, but we don't have cache coherence for invalidations. We have message passing, right? And they speculate that the rule should still apply for message passing, but that's really unclear. And there's been a lot of work on commutative concurrency control for databases. So how do we leverage commutativity when we're executing transactions? I'm not sure how the rule fits in with this. I really don't know. And it's something that's really interesting to think about. And so here are some examples of that and some of the work that this rule draws on. So this guy, Bill Weil, at MIT like 30 years ago, did a bunch of work on commutative abstract data types. Patrick ONeil in databases has worked on something called the escrow transactional method, which takes advantage of using commutative locking. Martin Renard, also from MIT, has done work on parallelizing compilers using commutativity. So commutativity is extremely powerful and has been used in a lot of different contexts, and I think there's still a lot of different ways that we can apply it. And then finally, my own work, had to throw this in here. So we use commutativity to execute transactions efficiently on a highly multi-core database. Actually the same 80-core machine that Austin used. We make commutative conflicting operations happen in parallel. All right, cool. So that's all that I have. Thank you for being a nice, attentive audience. And yeah, that's it. Take questions. All right, you've got your hand up. Yeah, what's up?
So, a couple of questions. The first one was when you showed all these operations that happened during the whole process. A lot of the operations, we don't know whether they are commutative or not until this operation is completed. So how does...
So that's why the definition of commutativity was so formal and weird, the whole X, Y, Z part. The point is that you're right. You don't know if something's commutative until you know what Z is. And so that's why they define Y more strictly than necessary, which is to say a region Y is sim-commutative if no matter what the Z is afterwards, it still commutes. And you can tell this by the specification. Like if there's no way to read something, then you can never tell that something happened in two different orders.
Thank you.
Yep.
So one thing that the paper wasn't exactly clear on is in TestGen, when it does the conflict coverage, does it just punt all that work to the SMT solver, or how does it do it?
I have no idea. Sorry. I don't know how TestGen works. I think you know more than me at this point, Tom. Sorry. But if you figure it out, you should let us know. Does anyone else know? Did they look into TestGen? No. Sorry.
Thanks anyway.
This might be a little tangential, but why? What is the reason that POSIX defines that the file descriptor has to be the lowest number?
I also have no idea why that is. I don't know if anyone here knows like the history of that, why that's the case. Oh, someone does.
If you use to replace standard out, standard in, you can kind of close those, and it's old. Old school.
Yeah, the problem is there are programs that rely on this behavior. You can't just throw it out the window.
Most of the processes are retroactively defined based on frequency behavior, so you can't guarantee that it wasn't required.
I actually did have a question too, which is
Okay.
in the presence of synchronized clocks, is there still have you guys done any? You mentioned your colleague who was looking at, machines with like fully synchronized clocks. Are there opportunities for like scalability that take advantage of both of these, like?
They take advantage of what?
Of both these techniques, like.
Yeah, so I think that there's a lot to do if you have synchronized clocks. Synchronized clocks make everything a lot better, and sort of the way that I think about that is that with synchronized clocks, you can timestamp operations, and once you've timestamp operations, you've almost made them commutative because you know later on what order to execute them in. Like, you can sort of like pile them up in any order and then sort them by their timestamp and execute them in the right order. So that's one way that synchronized clocks make things a lot easier because they give you that order. But that doesn't necessarily mean that you're going to have like a performant implementation if you just have to do all the work later, right? Yeah.
So you talked about the constructive proof being specific to a certain history. That's one part that I actually had a lot of trouble with. How specific of a history do you have to construct such an implementation?
So
like,
one
is
thing,
there a way to make, I don't know, is there a way to make that at all practical, or do I have to like upfront say,
so
I'm
you
gonna
should
rename
never
X to
use
Y?
the implementation that you'd construct from the proof. That is not something that should ever be implemented, okay? The only reason that they do that is to show that there is at least one such implementation. It happens to be this really weird one that they made work for anything, but it's also very specific to what happens. But the point is that one exists, and usually in practice, you can get one that's more general and more useful than the one in the proof.
Sure. I mean, so like, I guess what I'm asking is, if I want to use their construction, I have to specify like, I'm going to rename X to Y and Z to W. Please make me an implementation that will scale for that region.
That's the way the proof works,
okay.
yeah. Yeah.
Thanks.
Do you know of any more development-friendly, I guess, tooling around this? And I'm thinking more of, I guess, a type system that would kind of help the programmer enforce some commutativity, or the tooling embedded at the language runtime or at the compiler.
Yeah, I don't really know very much about that. I'm sure that work has been done in this area, but I'm not aware of that work.
One of the examples that you had in your presentation for when two things were not commutative was the one that had a seek to a specific file, speaks a specific offset, and then writing the same data. Why are those two operations, if they are writing the same data to the same place, not commutative?
Yeah, I'm not exactly sure. I can't remember exactly why that is. Someone here might know exactly why pwrite does that. It looks like, nope, okay. I would have to go back and look to remember why that is. But we could look at the specification and figure it out. Did you have a question? Any more questions?
Isn't it because one thread's already created the file, and then the other comes in and already in front of it goes?
But it's the same data. If it's the same data at the same offset, why is it not commutative?
I think the idea was that it should be commutative, but their implementation wasn't.
Oh, okay.
What was that?
I think the idea was that those two things should be commutative, but it's hard to imagine an implementation that would realize that without somehow coordinating.
Oh,
between
yeah,
threads.
yeah, that's a good point. That's right. Yeah, that's true. Sorry. So it turns out we were thinking about this a little bit incorrectly. It's not the case that it's not commutative. Where was this? It's that you probably wouldn't want an implementation that is scalable for that. You would want to just coordinate. That's two pwrites of the same data to the same offset.
So this was done on the syscall level. If you were
Yes.
to go, say, to like the ISA level, has anybody looked at that, or like how would that change?
I do
semantics?
not know. I have no idea. That's a good question. I mean, definitely what level of your interface are you working with is a really good question as well. Yeah. And it seems to me that the higher the level, the more opportunities for commutativity there are. Any other questions?
So, are you familiar with any work that the group's done with syscall rewriting?
Nope. Tom, you're killing me, man. Syscall rewriting, like in what sense?
So, like, Illumos Gate does the syscall rewriting for, like, LX brands and things like that.
Oh yeah, no, I'm not familiar with that work.
Yeah.
Sorry.
I was just
Maybe
wondering
you
if,
are.
like-
Do you want to talk about it?
Well, I think something that might be really interesting is to rewrite syscall call table on the fly to enforce commutativity invariance.
That's interesting. Yeah, I don't know. That
To
sounds-
fix broken operating systems like Linux.
So I'm not sure if this question makes sense, but I'm getting a sense that there is a trade-off between performance and scalability. Is that true?
Not always, I don't think. Yeah, I don't think that I could say one way or the other. at
Okay, 'cause it
least.
sounds like some of the scalability options actually seem to compromise performance.
They
at some
do,
level.
yes, but some don't. So yeah, it's just something that's scalable is not necessarily always going to give you the best performance. Actually, just to say one more thing about that, I think that's actually really important. It's something being non-scalable inherently is not necessarily bad. It might be the fastest performing thing you've got, and so. Right, for sure, exactly. If you're on one core, then scalability means nothing. But also, coordination isn't necessarily like a bad word. It's very reasonable to coordinate a lot of the times. We need to do that. The trick is to do it well. Yeah. Yeah.
So, when you're talking about the reverse of the rule, whether or not non-commutative operations can be scalable, you said that there are trivial examples where that's true, but I can't think of one.
Oh gosh, there's one in Austin's thesis that I can't remember. Yeah, I would have to go back and look. Sorry, I don't remember the example off the top of my head. All right, cool. Well, I'll be around for a little while after if you guys want to talk. Thank you.